In this video, we'll wrap up electrical communication, nerve behavior. I wanted to at least make passing mention of the property of electrical communication in that it allows for learning. So learning is something that you could spend an entire semester on, and we don't have that kind of time. So I'll just give you an example of a very, very simple kind of mechanism by which a synapse can learn, meaning that a previous firing can be remembered by the electrical circuit in such a way that the next firing event will be easier, more readily achieved. And to do that, we have to invoke a little bit more sophisticated receptor type. And the classic learning type receptor and the neurotransmitter most associated with learning is glutamate and the glutamate receptor. There are actually multiple types of glutamate receptors, and they go by a couple of them go by these names: NMDA and AMPA, the so-called AMPA and NMDA receptor. So these are agonists; these are pharmacological agents that stimulate the receptors. It is not the neurotransmitter that is actually being transported or being recognized by the neurotransmitter receptor. AMPA is a glutamate sensitive sodium channel, so a fast receptor. NMDA receptor is a sodium and calcium channel that is opened in the presence of the neurotransmitter glutamate. This convention, by the way, of naming receptors after agonists as opposed to the neurotransmitter or the ion, for example, is very common in pharmacology, so that you sometimes hear the GABA receptor. GABA is the actual neurotransmitter, but the receptor is referred to as the benzodiazepine receptor, because benzodiazepine is the agonist that pays the bills. It's what Xanax is. So it's very common that these receptors are named after the pharmacological agonist and not the neurotransmitter. Anyway, let's get back to learning. So here's a synapse that features both of those types of glutamate receptors, and this is glutamate as the neurotransmitter that has been released. So at time 0, with only, let's say, 3 molecules of glutamate released for the first time into this synapse, the postsynaptic cell is polarized. It has the resting potential. But here is a glutamate active responding sodium channel, the AMPA receptor. So when glutamate binds to it, it will open, leading to the depolarization triggered by the movement of sodium into the postsynaptic cell. That depolarization is shown here. The NMDA receptor initially is not opened by that release of glutamate because there's a magnesium ion sitting in the pore. But magnesium has 2 positive charges, right? So that depolarization is going to trigger a repulsion of these positive charges that cause the magnesium to be released out into the synapse, essentially opening that pore. So now we have, as a second event triggered by the release of neurotransmitter glutamate into the synapse, we now have the opening of the NMDA receptor. That receptor, as I mentioned, is a sodium calcium channel when it's opened. So now we have a sodium influx that triggers further depolarization of that cell, but we also have a calcium spike. Calcium spikes do what they always do, so you can trigger exactly the same response that you triggered with phospholipase C back in the previous signaling section. So you can have the fast-acting depolarizations accompanied by potentially much longer-lasting calcium effects: activation of protein kinase C, activation of calcium calmodulin, changes in gene expression, and in particular in this case, in a phenomenon that's referred to, or is one example of long-term potentiation, that calcium spike triggers the activation of the gene for the AMPA receptor. So you get the synthesis of more of that voltage-gated sodium or glutamate-gated sodium channel brought to the surface of the membrane. So by the time you've gotten to this stage of the process, triggered by the influx of calcium, you have a synapse that's much more sensitive to glutamate, So this synapse has learned, essentially. It remembers the fact that it is already fired because the NMDA channel became open as a result of the movement of that magnesium ion out. So we can say that the NMDA receptor is capable of something that is not unique to the NMDA receptors, but it's a term that's referred to as coincidence detection. It's able to determine the coincidence of A, glutamate in the synapse, B, a previous depolarization that was actually achieved by this particular AMPA receptor. So it has learned that there has been a previous depolarization, and this synapse is now much more sensitive. So that's a very simple neural circuit that just by adding one additional ingredient, that magnesium associated coincidence detection property of the NMDA, plus the calcium translocation that triggers potentially long-term effects through those signaling pathways, you get the ability to teach neural circuits to respond to the previous activation. So this is just one simple example of what is a whole lot of very, very potentially complex mechanisms that are associated with learning. But we'll stop there.